Welcome to this lecture on differential equations. Today, we'll solve the differential equation. Y prime of t equals y times quantity y minus 2 for t greater than or equal to 0. We'll study both the direction field of this equation and find its general solution. Let's first understand what type of differential equation this is. This is a first-order differential equation because it only involves the first derivative of y. It's nonlinear because y appears with a power greater than 1 when we expand the right side. And importantly, it's separable, which means we can separate the variables y and t to different sides of the equation. Before we solve this equation algebraically, let's first visualize its direction field to get some intuition about the behavior of its solutions. A direction field, also called a slope field, shows the slope of the solution curve at various points in the ty plane. Since y prime equals the slope of the solution curve, and y prime equals y times quantity y minus 2, we can plot these slopes as small line segments. Looking at this direction field, we can observe some interesting patterns. First, notice that when y equals 0 or y equals 2, the slopes are 0. These are called equilibrium solutions or critical points. Let me highlight these horizontal lines where y equals 0 and y equals 2. We can also see the behavior of solutions in different regions. When y is less than 0, the slopes are positive, indicating solutions are increasing. When y is between 0 and 2, the slopes are negative, so solutions are decreasing. And when y is greater than 2, the slopes are positive again, so solutions are increasing. Let's now trace a few solution curves following these direction fields. Let's trace some solution curves on our direction field. Here's a solution starting below y equals 0. Here's one starting between 0 and 2. And here's one starting above 2. Now that we have a visual understanding of the behavior of solutions, let's solve this differential equation analytically. Step 1. We separate the variables by moving all terms with y to one side and all terms with t to the other side. Step 2. We need to use partial fractions to decompose the left side of our equation. The expression 1 over y times quantity y minus 2 can be written as a over y plus b over y minus 2, where a and b are constants we need to determine. To find a and b, we get a common denominator. 1 equals a times quantity y minus 2 plus b times y. When we plug in y equals 0, we get 1 equals a times negative 2, so a equals negative 1/2. And when we plug in y equals 2, we get 1 equals b times 2, so b equals 1/2. Step 3. Now we can integrate both sides of our equation. We have negative 1/2 times the integral of 1 over y dy plus 1/2 times the integral of 1 over y minus 2 dy equals the integral of dt. Using the properties of logarithms, we get negative 1/2 times the natural log of the absolute value of y plus 1/2 times the natural log of the absolute value of y minus 2 equals t plus some constant c. Step 4. Let's simplify our solution. Using logarithm properties, we can combine these terms to get 1/2 times the natural log of the absolute value of the fraction y minus 2 over y equals t plus c. Multiplying both sides by 2, we get the natural log of the absolute value of the fraction y minus 2 over y equals 2t plus a new constant c sub 1. When we exponentiate both sides, we get the absolute value of the fraction y minus 2 over y equals e raised to the quantity 2t plus c sub 1, which we can write as k times e to the 2t, where k is e to the c sub 1. Step 5. Finally, let's solve for y. We have y minus 2 equals c times y times e to the 2t. Rearranging to isolate y, we get y minus c y e to the 2t equals 2. Factoring out y, we get y times the quantity 1 minus c e to the 2t equals 2. Therefore, y equals 2 divided by the quantity 1 minus c e to the 2t, which is our general solution. Let's verify our solution by looking at some specific cases. Our general solution is y equals 2 divided by the quantity 1 minus c e to the 2t, where c is determined by the initial condition. When c equals 0, y equals 2, which is one of our equilibrium solutions. When c approaches infinity, y approaches 0, our other equilibrium solution. This matches what we observed in the direction field, confirming our analytical solution. In summary, we've solved the differential equation y prime equals y times quantity y minus 2 both visually and analytically. The direction field gave us intuition about the behavior of solutions, and our analytical work confirmed these observations with the general solution y equals 2 divided by the quantity 1 minus c e to the 2t. Thanks for watching, and I hope this helps you understand differential equations better.